So in previous video, we introduced and we proved the Carathy-Doris theorem. And that is the first step about constructing a measure. And I'm going to introduce another theorem, proposition 1.13, which is kind of like the second step towards constructing a measure. So let's state the proposition. Notice that the way that we firstly define outer measures using a function rho that satisfies certain property. Empty set is in row, X is in row, and row empty set is equal to 0. And then Carathy-Doris theorem is based on the definition of that, the definition of outer measure of that using the function rho. Now what we're doing is we're going to introduce the connection between the outer measure and algebra. And later in proposition 14, which is kind of like the last step of constructing measure, is to further link the outer measure with algebra. Okay, so let's look at proposition 1.13. So if mu naught is a premeasure on the algebra A, and mu star is equal to, for example, mu star of E is equal to infimum of infinite summation of mu naught of EJ, where EJ is in A. And then E, okay, let's use A. And A is a subset of union 1 to infinity of EJ. Okay, so if we have this is a premeasure A and we define the outer measure in this way, notice that before our outer measure definition here is function rho, and here rho is a Hess domain and the elementary function. Okay, and so claim 1 is mu, outer measure mu on A is equal to the premeasure mu naught. And then the claim 2 is equal to every set in A is mu star measurable. Right? Every set in A is mu star measurable. Okay, how do I prove this? So let's prove claim A, claim 1. So pick A in A. We want to show mu star on A of we want to show mu star of A is equal to mu naught of A. How do we show that? Okay, let's write down the mu star of A. So one inequality is obvious, but let's just write down the definition for mu star of A. Let me copy it. Okay. Mm. And because this is so this is smaller equal than mu start of EJ, where E1 is equal to A and EJ is equal to empty set for all J is equal to 2. Right? Because this is one element in this collection, and the increment of the collection is definitely smaller equal than each one element of this collection. So remains to show mu star of A is larger or equal than the infinite series mu naught of EJ. How do we show that? How do we show that? Notice if this measure is infinity, then we have then we're done. If mu star of A is finite, then for all epsilon there exists for all epsilon there exists EJ in A such that mu star such that summation mu naught of EJ 1 to infinity is going to be smaller equal than mu star of A plus epsilon. Okay. Sorry, let me just add one more detail here. This is equal to mu naught of A. Okay. So we need to show this is larger than mu naught of A. Okay. So we have this inequality. How do we use that, right? How do we use that? So let's rethink about the proof of the other inequality. I think there is a trick that I wasn't aware of. So now I'm reading the proof info line. So again, we want to show this, right? And we assume it is finite. So let's pick E is in A. Right. And sorry. Let's suppose E is a union of AJ, where AJ is in A. And notice this union may not be a collection, may not be union of set, may not be union of disjoint set, but we can always disjointify them. So set B1 is equal to A1, B2 is equal to A2 set minus A1, you saw this many times, and Bn is equal to An set minus union 1 to n of Aj. Okay, good. So we have Bn n is equal to 1 to infinity is a sequence of these joint sets, right? And union of Aj is equal to union of Bn. That's J and here it's n. Okay, and so E intersect Bn is also a sequence of disjoint sets. So mu naught of E is equal to mu naught of E intersect union of Aj, which is equal to mu naught E intersect union of Bn, which is equal to mu naught union E intersect Bn. Okay, and so 1 to infinity, sorry. And let me think how to, right. So as we observe, this is actually just equal to E, right? And because E is in A, wait. So therefore, this infinite series is in A, and because it's infinite series in A by definition of Premeasure, whenever the infinite series in A, we can use the subadditivity, which is equal to 1. We can use countable additivity, which is 1 to infinity mu naught E intersect Bn. And recall how we define Bn. So this is equal to smaller equals n, mu naught of E intersect An. Okay, because An is equal to, because Bn is equal to An set minus something. And of course, this is smaller equals 1 infinity mu naught E intersect, or we can just say An. Are we done? Right, we're done. Since mu naught of E is equal to infimum summation 1 to infinity mu naught of An. An is in A. E is a subset of union of An 1 to infinity. And so what do we have here is we have mu naught of E is smaller equal than summation 1 to infinity mu naught of An for every An such that an is in A and E the subset of 1 to infinity of an. Hence, mu naught of E is going to be smaller or equal than the infimum of this set. Therefore, mu naught of E is equal to smaller or equal than mu star of E. And together, what we have is we have equality. So hence, whenever you choose E, you have mu naught E is equal to mu star of E. And then that finish our first claim. And then for the second claim, so every set in A, the algebra A is mu star measurable. So let's pick A in let's pick E. Oh, or A, sorry, A in A. And we want to show that A is mu star measurable. And once you have that is mu star measurable using the definitions, right? For all E that a subset of X, mu star of E is equal to mu star of E intersect A plus mu star of E intersect AC. And all we need to show is we need to show one-side inequality. Right, okay. Well, again, if this is equal to infinity, then we're done. So assume mu star of E is finite. Then for all epsilon, there exists Bj 1 to infinity, where Bj is in A, and E is a subset of union of Bj. And we know we have that summation mu naught of Bj 1 to infinity smaller or equal than mu naught of E plus epsilon. Right. So mu star of E plus epsilon is larger or equal than 1 to infinity mu naught of Bj. Let's see. One to infinity mu naught of Bj intersect with A plus mu naught Bj intersect with AC, which is equal to right. Okay, so I'm gonna I feel like I'm not very familiar with playing around with the definition of infimum. So we have this, and then we have so which is larger than infimum of. So let's think about this. BJs is a union of collection. They are not necessarily disjoint. Right. So let's see. BJ union of BJ. So notice that union of BJ A is intersect of that. Right. So notice that what's the relationship between E and BJ? E is a subset of BJ, right? Yes. And E intersect A is a subset of the union of BJ intersect A. So and this is equal to union of BJ intersect A, right? And this is one of the possibilities. So it is actually inside of the collection. You can write because BJ is in A, and I think A is also in A, right? And then finite intersection is still in the algebra, so BJ intersect A is in A. Okay, so this corresponding to summation 1 to infinity of mu naught of BJ intersect A, right? So this is larger or equal than infimum of E intersect A. And then similarly on this side, the infimum of E intersect AC. But what is that? That is mu naught of E intersect A plus mu naught E intersect AC. And then take epsilon goes to 0. We obtain mu star of E is larger or equal than mu star E intersect A plus mu star intersect E, and together we have equality obtained. Therefore, when we have A is mu star measurable. 3D. Actually, before I end up the video, I want to do a quick summary because I feel that overall, even though I finished this proof, there are still some pieces that I'm not very familiar with. So let's just go over and then make a summary together. So let's just review what we have done so far. We have defined order measure. Firstly, using the function rho, where rho has domain elementary family of sets. And then it will map to 0, infinity, including 0 and infinity. And then we have proved theorem 1.11 Cairesi-Doré theorem. And that tells us, what does that tell us? That tells us that if I have a measure, if I have an outer measure, then the collection of mu star measurable set form a sigma algebra, and mu star measure and mu star restricted on M is a complete measure. So we proved that. And in this theorem, so before introducing the theorem 1.13, which is proven over in this video, Folan introduced a formal definition for outer measure where we replace a function rho with a function mu naught, where mu naught is a pre-measure on the algebra A. And therefore, in proposition 1.13, you can see some connections between outer measure and the pre-measure and algebra. So the theorem is saying that if we have mu naught as a pre-measure of our algebra, then mu star is actually, and the mu star is an outer measure defined in the way using mu naught. Then mu star restricted on the algebra coincide with mu naught. In other words, mu star extends mu naught. And the second thing is every measurable, every set in the algebra A is a subset of is mu star measurable. So those are two claims we want to prove. And to prove first one, let's see. Okay. So to prove first one, we want to show that mu star restricted on the algebra coincide with mu naught, right? How do we show that? We pick a set A in. So first of all, we observe. So we pick a set A in the algebra, and we try to show mu star of that set A is equal to mu naught of A. And notice that one inequality is obvious because, and I think it is a inequality that mu star of A is smaller or equal than mu naught of A, because if you consider if you consider sequence of sets where the first element is A and all the other elements are empty set, then then A is definitely inside of this union, and each element of this each element of this collection belongs to algebra A. And therefore, the infinite summation from 1 to infinity all the way of mu naught of EJ, where E1 is equal to A and EJ is equal to empty set for all J larger or equal than 2. It is equal to mu naught of A, and because right. So mu naught, and that is one element inside of the collection, the infimum collection, like the infimum of a collection, right? And then mu naught of A is one element when you're comparing with all the others. And mu star is the infimum of that. So of course, mu star of A is smaller than mu naught of A. And the other direction is a little bit more complicated and need good observations. So the first, so we want to show that mu star of A is larger or equal than mu naught of A, right? And how do we show that? Okay, so we use the trick that so recall eventually what we want to show. We want to show that mu star of A is larger than mu naught of A. And equivalently, we can show mu naught of A is smaller or equal than mu star of A. And what is mu star of A? Mu star of A, right? I'm doing what I'm doing. I'm looking backwards, basically. So, sorry, here I think I use a different notation. Right. So here I use notation A to denote a set in the algebra. And here I use notation E to denote that let's see, to denote the subset of algebra. And so eventually what do we want to show? Because we want to show that mu naught of E is smaller or equal than mu star of E. And we know that mu star of E is equal to the infimum of a collection of elements, right? And the trick here is that if we can show mu naught of E is smaller or equal than all possibilities of this, from 1 to infinity for all EJ in this collection, and EJ is in the algebra and E is the subset of union of algebra. So once we do that, we can, so once we show it is smaller or equal than all possible elements in that collection, it definitely smaller or equal than the infimum of that. So our goal is actually to choose a random, to choose an arbitrary element from that infimum collection. So if you look at this, right, and we're actually trying to just pick an arbitrary thing from this collection, and we're showing that mu naught of E is smaller or equal than this this arbitrary element in this collection. And that's why at the very beginning, we pick E in this, and we are saying that, okay, choose an arbitrary union, arbitrary sequence of collections such that E is in the union of this AJ, and AJ, each AJ belongs to the algebra A. So that is arbitrary. That will lead us to have an arbitrary element in that infimum collection, and that's what we want. So that's why we are doing this. Okay, so because the union of AJ, they're not disjoint, right? And we like disjoint sets, so we can disjointify. So therefore, we actually redefine a sequence. So once we have an arbitrary sequence such that E is a subset of the union of that sequence, and each element of a sequence in the algebra A, we can define a new sequence such that it is disjoint and the union are equal to the union of AJ. So therefore, we do like B1 is equal to A1 and Bn is equal to An, or if you like, so B1 is equal to A1 and J is equal to AJ set minus I is equal to 1 to J of AI. So that's one way to disjoint, right? And then once you disjoint that, and then E intersect union of AJ, and because the union of AJ is equal to the union of BJ's, so it's the same. They're the same sets. And then therefore, let's keep closer look at. So mu naught of E, you write this on the left hand side, and it is equal to this, right? And you can rewrite this because those union are equal, and you can rewrite this, right? You can rewrite this, and then because this is E, and we know that E belongs to the algebra, so so this infinite series belongs to the algebra A. And then if you recall the definition of premeasure, like as long as we're given that infinite union of sets, it belongs to the algebra, then the countable additivity counts. And those are disjoint, of course. So therefore, we can use the countable additivity of the premeasure. And then once we have this, and what else do we have? Because En is really a subset of An by the way we construct Bn, because Bn is equal to An set minus some set, right? So this inequality holds. And this is inequality is smaller or equal than A because E intersect A is a subset of An. Okay, and then once you have that, let's see. Once you have that, so you have mu naught of E is smaller or equal to, okay, cool. And then because this is arbitrary, right? So this set is arbitrary from arbitrary candidate in the collection of the of this infimum collection. Therefore, no matter what type of elements appear in this collection is going to be larger or equal than mu naught of E. And therefore, infimum of them is larger or equal than that. And what is infimum? Well, the infimum of that is just the mu star of E. And therefore, we obtain the other inequality and we're done. So if I want to highlight the tricks, I think I would highlight, so this part is definitely something that I am not very good at, to observe and to know that we need this disjointness collection. And then also I'm not familiar with at the beginning choose a random because we want to show this. I think these are techniques that I need to make better observation. And also I need to remember that the fact that if I have infinite series inside of my algebra, then the counterparativity works for our for the pre-measure. Okay, and then we have and then the second claim is that if we have a if we have A that is in the algebra A, then A is mu star measurable. So you want to prove that, and then you can think about how definition for mu star measurable, right? You prove that definition, and notice that one direction is trivial, and then we just need to show the other direction. So that is direction. So this direction. And then also because this is if this is infinity, then we're done. So we're proving this is less than infinity, right? And how do we prove that it's less than infinity? When it is less than infinity, by the definition of infimum, we can actually find a specific. So given that epsilon, we can find a specific collection of sets such that satisfies this inequality. And would we use that inequality? That is a good question. So how do we use that inequality? I think this is a part that I will guess that I got stuck when I was first working on this problem. So we have this, and because what do we want? We want this direction of inequality, and we have this, right? And then let's just put it on the left-hand side, and we're trying to work in like this way. So that's why I put it on the right-hand side. And we know this is larger or equal than this. And because this is larger or equal than this, and let's think about what's special about the mu naught bj. Well, mu naught bj, because eventually I want to do this, right? And then what's the difference between this and this? Well, it does not have E, this one does not have E, this one does not have A. So at least let's bring just one element in this so we can work with E and A, right? So this is equal to intersect A, intersect AC. So I think the way of thinking this is a little bit hard for me. So okay, we have this. Okay, so we have this, right? And then what else do we have? So if we have mu j, okay, so notice that this, because the bj and because of this, you're thinking about the connection between the union of bj with E, right? So we have this. Okay, what kind of connection can we get by looking at those two facts, right? So this is equal to right. So this is equal to this. And do we have subjectivity? Well, beaches are not technically disjoint, so we don't know, but we know it must be larger or equal than the union of BJ intersect A. Well, what is the union of BJ intersect A? It's going to be larger or equal than E intersect A because union BJ intersect A, because union BJ contains E. So union BJ intersect A is definitely contains E intersect A. So we have this inequality. And then we have these inequalities, right? And then why do I want infimum? Let's see. Sorry, I'm not sleepy. Let's think about this. BJ E intersect A, which is subset with union BJ intersect A, which is equal to this, right? BJ infimum. I think that makes sense too. Let's see. Because right, because what I want to say here is that this is um Let me think about this. Union intersect A. So because we know that the union of this is in A, the intersection, so this term is in algebra because A is in algebra, right? And A is and A, no, A is not technically inside of BJ. So I cannot really say, I cannot really use the countable additivity of Premeasure because I'm not sure whether or not this is inside of that. Okay. So we definitely know this is larger or equal than mu naught of this. And the mu naught of this is larger than mu naught of E intersect A. But that doesn't help us because we want to connect with U star. Intersect. So what I'm going to do is going to delete this up because it doesn't make sense. So I think I know what I was thinking. So we have this, right? And we have this, and right, and more explicitly, we have this. And notice that E intersect A belongs to this. Why? Because E is a subset of union of BJ. Therefore, this is actually one candidate of infimum collection, where each element satisfies that E intersect A is a subset of the union of that collection. So this is definitely such collection. And therefore we have, and then therefore one element from that collection is definitely larger or equal than infimum of the collection because you're comparing it, you are finding the minimum one, right? And which is infimum of that collection is going to mu star E intersect A. And similarly for this, we have this, right? And therefore we obtain this inequality if we let epsilon goes to arbitrarily small, and therefore A is mu star measurable. Sorry about the I think I caused some confusion by using different notations and going back and forth. But I hope this is clear for you. Thanks for watching.